Hello Internet! So today we're going full SSA. This video doesn't add any language features. SSA is a representation change, and the payoff comes later in C3 when we start optimizing. But this move has to happen first. Quick recap. The series is 5 toy compilers, and I'm learning SSA from the ground up to decide whether to adapt it into my real C compiler. C0 was a CFG. C1 added 3 address code. Today is C2, the SSA. So what is SSA exactly? Static single assignment. Every value gets exactly one name. Write to a variable twice in the source and you get 2 different names, say x1 and x2. Every read points at exactly one of them. The IR literally tells you which. In straight line code, this is easy. 3 writes, 3 names. x1, x2, x3, and you're done. The interesting case is branches. 2 writes reach the print. At source level, both are x, and the actual branch is decided at runtime. SSA needs a name for that too. Whatever value reaches the print is a new SSA name. We can call it x3, and its definition needs to say x3 is x1 if we came through the true branch, and x2 if we came through the false branch. The merge has to be written down. That construct has a name. It's called a phi node, or in C2's encoding, a block parameter. Same idea, slightly different shape. So that's SSA. Each value uniquely named, each merge made explicit. Same move as C1, one layer up. C1 made intermediate values explicit. C2 makes a link from each read to its assignment explicit. Okay, so that's the IR we want, every value uniquely named. Merges are written down. The question is, how do we build it? We have an AST. We've turned it into a CFG. Now we want to turn that into SSA. The challenge is, at every point in the CFG, we need to know which variables had different writes on the incoming paths so we know where to put the phis. And once we've put a phi, that phi is itself a new definition, which might force more phis at downstream joins. We don't want just any SSA. We want a minimal SSA. No phis we don't actually need. Without that, you could just place a phi at every block for every variable. Correct, but absurdly wasteful. Minimal place is what makes phi positioning an algorithm design problem in the first place. The traditional algorithm for this comes from a 1991 paper by Citron et al. It involves dominator trees, several passes, and a lot of machinery. I'm not going to dig into the mechanics today because we're not going to use it, but it's been the standard for decades. Clang and GCC both use variations of it. But it turns out there's an easier way to get essentially the same result. In 2013, Matthias Braun et al. Published a paper titled Simple and Efficient Construction of SSA Form. And the central claim was, you don't need any of that. You don't need dominators. You don't need frontiers. You can build SSA in a single pass over the CFG as you're emitting it in about 100 lines. It almost feels like the natural approach you'd come up with if you sat down to build SSA from first principles. What the paper adds is the proof that this approach is correct and produces minimal SSA, at least for reducible CFGs, which covers almost everything. Every block holds a map, current def. It answers the question, for each source variable, what's the current SSA value at the end of this block? When you write to X, you update the map. When you read X, you ask the block. If the block knows, return the value, and you're done. If the block doesn't know, you look like the predecessors. If you have exactly one predecessor, you recurse by asking that one block upstream. If you have multiple predecessors, this is a merge point. You eagerly create a phi right there, and the phi's operands come from each predecessor. That handles the forward case if you never have to go backwards. There's a problem though. Loops. The loop header has 2 predecessors, the entry and the back edge from the body. When we read a variable at the header, we ask the predecessors, but the back edge hasn't been emitted yet. The body isn't built. So you have a chicken and egg problem. Braun's solution is a single primitive, the sealed block. A block is sealed once all of its predecessors are known. While a block is unsealed, reads create a phi eagerly as a placeholder and defer filling in its operands. When the block finally seals, any time after the last predecessor connects, you walk back through the predecessors and fill in the operands. That's the whole trick. No dominators, no frontiers, just 2 pieces of state per block. The current definition map and a sealed flag. Let me show you this in a real loop. We start in the entry block. The function parameter n is bound. We emit a const for I. So far, no phis, straight line code. We create the loop's head block. It's marked unsealed. The back edge from the body isn't there yet. Inside the head, we evaluate the loop condition, I less than n. Both I and n are read. The head is unsealed, so each read mints a phi as a placeholder. We don't know what the operands are yet. Both phis go into a list called incomplete phis. We emit the body, I equals I plus 1. The new value is bound in the body's map. The body terminates back to the head, and that's the back edge that completes the head's predecessor set. Now we seal the head, walk the incomplete phis. For each one, ask each predecessor what value flows in. The phi for I gets the const 0 from entry, and the incremented value from the body, two distinct operands. The phi for n gets n from the entry n again from the body, because the body never touched it. Two operands that resolve to the same value. And we're done. That's construction. Construction is done. Okay, so one detail. Look at the phi for n. Both incoming operands resolve to the same value. It's not actually doing anything. It's just passing a value through. This is what's called a trivial phi. Braun's algorithm creates them. They're a side effect of eagerly creating placeholder phis anytime we need it. One final pass cleans them up. Walk every phi. If the operands all reduce to one value, replace the phi with that value, propagate, and check the users. They might be trivial now too. Use a stack for the work list until there are no more trivial phis left. After this pass, what remains is a minimal SSA. Same output Citron's algorithm was produced for reducible CFGs, which the paper proves. For irreducible CFGs, there's a separate extension for full minimality. It involves computing strongly connected components, but I'm skipping that for now. About 100 lines of code total, no dominator trees in sight. So we have SSA. The IR is clean, but nothing actually has phi nodes, not CPUs, not WebAssembly. So we need to translate the phis back into normal assignments. This is called SSA destruction. For most phis, it's pretty simple. A phi at a join becomes a copy on each predecessor edge, and you're done. But there's a subtle case that can affect the correctness. This loop swaps two variables. In SSA form, the back edge to the loop header passes b comma a to the head's parameters a comma b. It's basically a swap of the two variables. So let's try the copy sequentially. The first assignment clobbers a value we needed for the second. The swap doesn't actually swap. This is the parallel copy hazard. The semantics of a phi is that all operands are bound simultaneously. Sequential copies don't have that property. The classical fix is temporaries. You read every value into a fresh local first, then write the temporaries into the destinations. It's always correct, but it costs roughly double the copies and double the number of local variables. C2 takes a different route. We add a source level statement, parallel assign. Left side identifiers, right side expressions. It does what you would imagine. Evaluate everything on the right, then bind everything on the left. Single statement, parallel semantics. And the elegant part is that at the WebAssembly level, this is free. To compile a parallel assign, we push every right-hand side onto the value stack, then pop into the left-hand side locals in reverse order. The stack discipline is the parallel copy primitive. There's no analysis, no temporaries, the hazard goes away. In C2's into AST, the lift from CFG back to AST, every multi-parameter edge becomes one parallel assign. The lifted output has no destruction temporaries anywhere. Okay, so what do we have now? Full SSA via Braun's construction, sealed blocks, eager phi placement, trivial phi cleanup, hazard-free destruction via parallel assign, lower to the WebAssembly value stack with 0 temporaries. Braun's construction itself is about 100 lines. The whole C2 compiler still fits in roughly 1,000. Look at the final lifted code. Locals are declared at the top. Parallel assign at each edge. Minimal phis, just the ones we actually need. The IR, what we work with internally, is genuinely cleaner. Every value has one definition. The output, on the other hand, we've had more locals than before. Parallel assign statements at every join, and the C0 while switch dispatcher is still wrapped around the whole thing. More bloat in the output. C3 is where we trade that bloat for actual savings. So next video, C3A. Originally, I planned C3 as one video covering optimizations, but it turned out to be too much for one slot, so I'm splitting it. C3A is a relooper, the pass that converts this dispatcher back into real while loops and if statements. Okay, so until next time.